Hello, everybody. This is Mr. Bear. I'm bringing to you the Skill 21 lesson about graphing exponential functions. All right, first of all, let's talk about what an exponential function looks like. We would write this as f of x equals a times b to the x, where x is a real number. And we're going to talk about what the a and the b do here. Okay, so let's start with, well, what does the b mean? Well, let's see. I'm going to look at the function y equals 2 to the x. If I look at negative 2, that means I'm going to have, sorry, I'm getting ahead of myself here. I'll have 2 to the negative 2, which would be the same as 1 over 2 squared if I use my exponent properties, which gives me 1/4. Okay, so at negative 2, I'm going to plot the point 1/4. So it's going to be way down here. If I plug in negative 1 for x, I have 2 to the negative 1, which is 1 over 2 to the first, so 1/2. So I go over to negative 1, I plot 1/2. 2 to the 0, you better know that 2 to the 0 makes 1, so 0, 1. The next one, 2 to the first, which is 2. And when x is 2, we have our y value of 2 to the second, which is 4. Okay, what do we notice about these dots? Well, it looks like they kind of start growing slowly. Then we start rising quickly. Okay, and in fact, if we look at the left-hand side, if we start plugging in smaller and smaller values for x, if I have like 2 to the negative 5, that'll be the same as 1 over 2 to the 5th, which is 1 over 32. If I have 2 to the negative 10, that's 1 over 2 to the 10th, which is like 1 over, I'm going to cheat because I don't know what 2 to the 10th is, 1024. So you can see that these values are getting smaller and smaller, but the fraction will never become 0. So we'll talk about this a little bit more in a minute, but we would say there is a horizontal asymptote here at x equals 0. Now let's also notice real quick this graph, when we look at it, as x is moving to the right towards positive infinity, we see that the graph is growing quickly. Okay, so when a graph looks like this, we'll call it growth. Okay. If we compare that then to a graph like y equals 1/2 to the x, if I look at this one, if I take 1/2 to the negative 2, that's the same as, I'm going to do a method that I call the flip and change. So I'm going to flip my 1/2 to 2 over 1 and change this sign. So negative 2 has a value of 4. If I plug in negative 1 for x, I'll use my flip and change. So when x is negative 1, y is 2. We know that 1/2 to the 0 will be 1. If I plug in 1, 1/2 to the first is just 1/2, so 1 comma 1/2. That right here. And if I plug in 2, 1/2 squared, that just means 1/2 times 1/2, which is 1/4. So what we noticed here is we were decreasing pretty quickly until we start to level off. Now, as I plug in larger and larger values for x, if I have like 1/2 to the 10th, that's the same as 1 over 2 to the 10th, which we know that's going to be a really small fraction. So once again, we're going to get an asymptote at 0. But the difference between this graph and what we had in the last one is, if you look at the last one, we started off really small and we grew as x went to the right. If we look at this situation, when x is to the left, so when x goes to negative infinity, the graph is growing, but as x goes to positive infinity, we see that the graph gets shorter and shorter and shorter, we're going to call this decay. Okay, so we would have decay. So when you look at the graph going to the right, if the graph is looking like it's going to level off, as it's doing here, then that means it's going to be decay. All right. All right, so now let's summarize this. All right, so for each of these, horizontal asymptote occurred at y equals 0. Looking at both of these, the y-intercept, well, on the first one, it was at positive 1. And on the second one, oh, it was still at positive 1. So we would say the y-intercept is at the ordered pair 0, 1. Let's talk about domain and range. When we talk about domain, we're talking about the x values. So when I look at each of these graphs, the graphs go on forever in the upward direction. Well, actually, that's describing range. For domain, we see arrows on both ends of the graph. So what that means is this graph is going to cover every possible x value. Same thing on this one. What that means is that any x value that you plug into the function is valid. So we would say that the domain is all real numbers. Okay. For the range is going to be the y values that we can have. Now, if you notice on both of these graphs, they never go below the x-axis. So we can't have negative y values. So for the range, we'd say y is greater than 0. Okay, it can't be equal to. The reason it can't be equal to is because we talked about no matter what you put in as your exponent, you're never going to have the function actually equal 0. It'll get closer and closer, but it won't actually ever equal 0. Okay? So in each of these situations, notice that on each of these equations, I only had the b part, okay? I didn't have a number like a multiplied in the front of it, so we'll pretend that those were 1s for a moment, okay? So in each of these, the b value, how does that affect the graph? When b was 2, the graph grew. It turns out that any time that the b value is greater than 1, the graph is growth. And we'll talk a lot more about this in the next lesson. It turns out when we had 1/2, we know that exponential functions, you have to have something greater than 0, because if our b value is 0, 0 to any power is 0. B value couldn't be equal to 1 because 1 to any power is just 1, so we wouldn't have any growth or decay. If our b value is between 0 and 1, the graph is decay. Okay. All right, so now we're going to talk about what happens when we have an a value in front of our function. All right, so if I had 3 times 2 to the x, well, what would that mean? That would mean 3 times 2 to the negative 2. So it'd be 3 times 1 over 2 squared, so 3 times a fourth, so 3/4. So at negative 2, I'd have 3/4. If I plug in negative 1, I'd have 3 times 2 to the negative 1, which would be 3 times 1/2. 3 times a half, half of 3 is 1.5. Or you could say 3/2. But I'm going to use 1.5 in my thought process, so it would be here. If I plug in 0, I have 3 times 2 to the 0, so that's going to be 3 times 1, which is 3. And then plugging in 1, I have 3 times 2 to the first, so that's 3 times 2, which is 6. So 1, 6. And next one, 3 times 2 squared, that'll be 3 times 4, which is 12. So I go over to 2 and up to 12, which puts me off the graph by just a tad. what you'll see is we have basically the same graph as our 2 to the x. It's just that it's going to be a little bit taller. So if we think about those transformation rules we learned, if we have an a value in the front, it should make the graph nicer and taller. But if we look at, well, we'll talk about what happens in addition to that when we look at the next graph, okay? But again, notice that we had a 2 for our b value, so this means growth. We'll talk about that a value in a moment, okay? Oh, let's also make note that the horizontal asymptote here is still going to be at 0. Okay, next one we have 2 times 2 to the x. So same kind of function, but now we just have an a value of 2. All right, when I plug in so 2 times 2 to the negative 2, that's going to be 2 times a fourth. So a fourth of 2 is a half. So negative 2 comma half. If I plug in negative 1, 2 times 2 to the negative 1, that's 2 times 1 half, which is 1. So negative 1, 1. If I plug in 0 for x, I have 2 times 2 to the 0, so 2 times 1, that gives us 2. 2 times 2 to the first, that gives me 2 times 2, which is 4. If I plug in 3, 2 times 2 to the third is 2 times, whoops, not 3, 2. 2 times 2 squared, so 2 times 4, which makes 8. All right, so we can see we have another function. It's growth. We can see our b equals 2, so it's growth. We still have a horizontal asymptote here at, whoops, I wanted to change the color there. Horizontal asymptote at 0, at y equals 0, that is. How does the graph of 2 times 2 to the x change from 3 times 2 to the x? Well, let's see. What did change? This one looks like it had a y-intercept at 3. This one looks like it had a y-intercept at 2. So let's see, this was a 2 and this was a 3, so it looks like the y-intercept changed. Whoops, I'm about to misspell intercept. So A affects the y-intercept. Okay? All right. So now what we're going to do is talk about how to shift exponential functions. To do this, we're going to utilize some of the transformation rules that we learned way back at the very beginning of the semester. So here's the general form for an exponential function. So we have a times b to the x plus h plus k. All right, so a is going to tell us that we are going to stretch or shrink. And it'll also give us a location for our y-intercept. However, the y-intercept will be affected by if we have this k value at the end, okay? So we'll have to kind of illustrate that when we look at the rest of this. The b is still going to tell us if the function is growth or decay. H is going to tell us that we shift left or right. Note that it does the opposite of what we think it would do. Mr. Bear always referred to this as a weird one. I don't know if Ms. Claywell did or not, but Mr. Bear always called those the weird ones because your ex, your ex is weird. If you've ever dated somebody and you broke up, you probably broke up because they were weird, or you want to think they're weird, so it justifies why you broke up with them, right? Anyway, k value is going to tell us that you shift up or down. Okay, so our a value, it won't directly tell us the y-intercept, but if you take your a value plus your k value, then you'll get your y-intercept, okay? So if my a value was at 2, but then I shifted the graph up 3, well, my y-intercept would go from 2 to 5, okay? So we'll kind of keep that in mind when we're looking at these, okay? All right, so knowing those transformation rules, we are going to practice now. So I have a function y equals 2 to the x minus 1 plus 4. We're going to first identify the transformations. So looking at this, I have a minus 1 with the x, so we're going to go right 1, and we're going to go up 4. The y-intercept originally on this, so we have to have an a value here, so the y-intercept is an understood 1 in front of this. So 1 times, or sorry, so 1 plus the 4. So we're going to have a y-intercept at 5, okay? So we'll write that as 0, 5. So I'm going to go ahead and plot that on my graph. Now this 4 is going to tell us our asymptote, so we'd have the equation y equals 4, so I'm going to go ahead and draw in that asymptote. And now we're going to go ahead and apply our graph, okay? Now, another thing I should have noted is that this function also has to shift right 1. So I identify my original y-intercept, and then what I'm going to do is shift it over 1. So when I do this finally, my graph will end up looking like this, okay? Something to this effect. And it's growth because of this 2. All right, so this is growth. For the domain of this function, well, it's always going to be all real numbers. The range here, since our asymptote is at 4, we have to say y is greater than 4. Okay? All right, let's try another one here. So for this one, we have this function. Again, we're going to assume there to be an a in the front, which will be 1. So I'm going to go ahead and figure out the y-intercept. The y-intercept is going to be that 1 minus 3. That's kind of where I'm going to start this. So I know I'll have a y-intercept at negative 2. I have a minus 3 for a value at the end. So that is going to tell us that we'd shift things down 3. Normally we'd be up here. We're shifting down 3. Our asymptote would normally be at 0, so now our asymptote is at negative 3. Okay, so our asymptote y is equal to negative 3. Looking at this, we also know that we have to shift left 2. That minus 3 told me to go down 3. So my normal y-intercept would be here. I have to shift it left 2. And this b value tells me that I have decay. So that means that my graph is going to decay. Oh, shoot. I lost my point there. There we go. So it's going to look something like this. Okay? The domain, of course, is still all real numbers. The range, of course, is going to be y is greater than negative 3. All right, so now you've got some basics. We'll spend some time together in class talking more about these specific pieces, okay?